Hey, math people, we're looking at lecture 3 of the second chapter of differential calculus, which is calculus 1. We're going to be looking at product and quotient rule today. We'll start with product, then we'll move to quotient. So remember, this video is for you, Anderson, or whatever your name is. So use the timestamps, click around, watch what you need. Okay, let's get to it. Let's math. Okay, so starting from the top, I want you to... So I guess we looked at this function in a last video. Take a look at this and take the derivative using the bad cat method. So I don't know. I didn't make this meme, but it's a good meme. Okay, so we don't like taking derivatives this way. So I mentioned that back with limits. If you were to apply properties with limits, it would kind of like behave as expected. That is not the case with derivatives. If you attempt to take the derivative of this expression, as of right now, we only have access to power rule, which is term by term. And as of right now, it is not expressed term by term. It's written as a product of two different binomials, right? So, in the last chapter, what we would do is we'd multiply this out and then use power rule for each term. If we want to just take the derivative in its current form, we have to get a little crafty. We need a special rule for that. So if you were to take the derivative in the incorrect way by just doing, oh, this is a 3, this is 0, this is 2x, and this is minus 4. You're not going to get the same answer. So I want to show that. I'm going to show that right here alongside the correct answer using distribution and then power rule. So 3, 2, 1. Here it is. If you were to just take the derivative of each term here, you're going to get like 6x minus 12. That's not the derivative of this expression. The one way we know that is that this is going to be cubic. 3x times x squared is 3x cubed. And the derivative of a cube is not a line. It's a quadratic of some sort. So what we have to do is we have to multiply this out and then just take the derivative term by term. Okay, so something's up. That's all we're really getting from this, is that we do not like these. We do not like, at least product we don't like, right? We don't like writing the derivative this way, and we don't like writing the derivative this way for quotients as well. That's going to be the second half. We're good to go with pluses in between, and we're good to go with minuses in between. This is like term by term. These are two separate functions written as separate like terms. Okay, so we need a special rule. It's called the product rule. I'll show one of the proofs for it a little bit later, but here's how the song goes. If you have a function here and a function here, some f of x and some g of x, what you would do is you would take the derivative of the first one and then keep the second expression of x the same, and then you would keep the first one the same and then take the derivative of the second. So in the example we just looked at, we would do, okay, derivative of the first factor, which is just 3, keep the second the same. So u prime is this 3 and v is this x squared minus 4x. This is u and this is v. So, and then we would add, okay, well, now keep the first one the same and then multiply that by the derivative of the second. So first one is the same here. And then the derivative of the second is 2x minus 4. Okay, this literally is the correct answer. If you were to multiply it out, combine like terms, you get that same 9x squared minus 20x minus 8 expression above. Voila, this is the product rule. So derivative of first, keep second, plus keep first, derivative of second. Let's do it. So yeah, like in both of these cases that we're going to look at, you could multiply it out. You could do that, and then just do term by term. But consider if you had like other functions in the way, like cosine or e to the x or natural log or whatever it may be, in which case you can't multiply it in. You can't say, oh, just distribute x into cosine. You need the product rule for those. So we're just looking at these algebraic expressions first. So feel free to pause. We're going to go over these in 3, 2, 1. So if we were to use product rule, we would do derivative of first, keep second, plus keep first, and then derivative of second. Product rule is not too bad. You can also make mistakes with product rule, and it's like fine, because if you were to just like flip-flop the order a little bit, multiplication is, what's the word, commutative, and same thing as addition. So you could just say take the derivative of the second and multiply it by the first, the first term, and then plus the vice versa. The only thing you can't mix and match is you can't mix and match the derivatives together and then the given function expressions together. You have to make sure they're paired in that way. Anyway, you end up getting, I guess, 9x squared plus 12x, and feel free to verify that if you were to distribute in that x squared. Sometimes doing algebra first is going to save you some time. All right, looking at the second one, it's derivative of first, keep second, and then keep the first, and then multiply by the derivative of the second. So just kind of following that ebb and flow. I got 2 more examples for you here. So here's one where we're looking for h prime of 0. I'm kind of jumping to the second one because this one's just kind of straightforward-ish. See if you can do this one on your own. 3, I'm not going to give you any hints there. But for 4, I'm giving you that h is just the product of f and g, and then I'm giving you these little snapshot moments of f and g. So see what you can do. 3, 2, 1. All right, for the first one, I didn't give you any hints. I just said, okay, do it. Well, if I have at 2x minus 5 squared, I have 2 of these things, right? So I'm really just writing that thing out twice, and then I'm just doing derivative of first, keep second, plus, okay, the derivative of the second and keep the first. You can multiply it out, you get 8x plus 20. For a lot of these, like, oh, okay, this is going to be quadratic. It makes sense the derivative is linear. Okay, with 4, well, we just straight up know the definition of the product rule. If h is just a product, what we can do is we can just write the product rule for h prime. So that would be like one last time, because I've said it a few times now, and like the hope and dream is that you do this enough times to a point where you like get like sick of either hearing yourself saying it, sick of me saying it, whatever, because then at that point maybe you have the rhythm down. So if I have h is the product, u and v, or in this case f and g, then h prime is just derivative of first, so you're going to hear me say it again, times the second plus keep the first, and then derivative of second. Okay. Looking at h prime of 0 then, I'm just plugging in 0 for each of these x's. Hey, I have f prime of 0, that's 2. Hey, I have g of 0, that's 3. Hey, I have f of 0, it's 1, and then g prime of 0 is 4. At that point, you can just do number stuff. 2 times 3 is 6, and 6 plus 4 is 10. Yeah, so this is kind of like a tabular approach. Like, what if I gave you like a table, or just, I like to say like snapshot moments, and then of course the first 3 were more what you would expect. If you're curious about the proof, here it is. Is it worth a heavy-winded explanation here? Not so much, I'm gonna guess. But you can read through it. There's proof. I don't know if it's worth talking too extensively about it. If you have any questions, feel free to write in the comments. But you just got to know that uv prime plus u prime v, right? That's just the product rule. Okay, so now let's reconsider another function we looked at the last lecture. So let's take this derivative using the bad cat math. So bad cat math looks like this, doing derivative of just top and then derivative of just bottom. That's not how you do it. So drawing the attention to that right now. It's going to look like this, right? So using bad math, if you did power rule up top and then just power rule down below, you get this expression right here, which is not correct. We did this problem in the last lecture, I guess, right? Yeah, it was like on the first page. And what you can do is you can just do algebra first. You can just divide each term by x, and you get that this expression is algebraically equivalent to 2x squared minus x, and then just power rule it up. These are not the same expressions, right? So we're going to use, I guess, method 2. Oh, wait, what? Oh, this is goofy. If you're curious, this is just another way of doing, that just seems like, this is this, but with extra steps. Yeah, like you can rewrite divide by x as 1 over x, and then do product rule off that. This is my fun way of showing you that like we're at this point of math now where like there are multiple approaches to the same question. I guess you can argue that you did that back in algebra. Like you can algebraically simplify things in different ways. But it kind of opens up quite a bit in Calc, which is why I love Calc. Okay, and which is why students kind of don't like it as much. But you'll get used to it. This course starts off really not fun. And then once you get familiar with all of these rules, you're kind of just using the same rules for a lot of the year. You're like, oh, okay. Like it's a little overwhelming at first. But once you see that we're really just kind of speed running through all the rules to the game, you know, like whenever you learn like you're at like a friend's house and you're learning how to play a board game, and then you're just like listening to their explanation and you're like, what are you talking about? You kind of just got to play the game. So let's play the game, you know? All right, here's quotient rule. The way it goes, if you have a u, so this is me explaining the rules to the game, and then we're going to play the game, I swear, in like 30 seconds. U over v. Here it is. It's v u prime minus u v prime over v squared, which is like what? I have like a spell-ish mantra to it. Low d high minus high d low all over low squared. Thinking, what are you talking about? Low being just on the denominator. D high, meaning the derivative of top, minus high, so just u, that's what's up top. D low, which is derivative of low, and then all over low squared. So how is that going to play out if we, so now let's play the game, right? If we use the function above, right? So we know the derivative is 4x minus 1. Here's how it goes. Low, so low is just x squared. And then d high, derivative of top, so that's power rule. That's 6x squared minus 2x. So right here, this is low. This is d high, low, d high, low, d high. And then minus high, so I'm just rewriting the top. The high being what's up top, or, you know, u. And then d low, derivative of x, is just 1, so that's power rule, right? So this is low, d high, minus high, d low, all over low squared, so x squared. If you then distribute out the top and then divide out the x squared from each of the terms, you get the same thing. By the way, sometimes algebra first is just strictly better. Like I probably wouldn't use quotient rule here, but it's a nice, this problem's like a nice vessel to like connect the bridge between the two. So low d high minus high d low all over low squared. Practice, play the game, right? So like for me, whenever someone's trying to explain the rules to a board game, I'm just like, man, can we just play like a round, right? Let's just play. I'll make mistakes. So play, make mistakes, and then we'll course adjust, okay? 3, 2, 1, here come the answers. Hopefully you paused and tried. Hopefully you're playing the game, right? Watching someone playing the game, you're not gonna be as good. All right, so way the song goes is low, d high, derivative of top, minus high, so that's just top, d low, power rule. And then this is all over that bottom, low squared. And then comes the algebra, right? So distribute the negative 10x, multiply the 5x squared and the 3x squared, and you get this expression right here after simplifying the numerator. Okay, we like this expression. So there are going to be eventually more approaches to these problems. Just keep in mind, like I don't know if I would use quotient rule for honestly either of these two in their current forms, but we're eventually going to get to a point where we learn new rules that can be in place of these. But anyway, it does work out just fine. If I do low d high here, low is just this quadratic. Derivative of 1 is 0, so this whole term goes away. And then minus high, which is the 1. D low, derivative of 3x squared is 6x all over low squared. It looks like this expression right here. All right, let's do another round. So these two will play like the last 3 and 4 for product rule. Try out one more. This one I definitely would product rule, by the way. The other two, I would use algebra first here for this one, and then just do power. And then for this one, I would do what's called chain rule. We'll eventually learn the chain rule. In this case, you got to use quotient for the record. So anyways, use quotient rule on 3, see if you can follow through that logic. And then 4 is going to play out like 4 with the product rule. So I'll leave it at that. 3, 2, 3, 2, 3, 2, 1. All right. Low d high minus high d low all over low squared. I'm not simplifying that. So on the, like if you're taking an AP course on the AP exam, if your expression is algebraically equivalent to the right answer on the free response, then you're good to go. You don't have to simplify it. So I generally say don't worry about simplifying some of these things. But don't tell that to your calculus teacher if they're otherwise. Don't say, but the guy I was watching online says I don't have to simplify. Some teachers will make you do that work. Sorry, and rest in peace if that is you. All right, for the next one here, J is defined as F over G, so that's literally just the definition, low d high minus high d low all over low squared. And then I have all these. They're all listed above. Plug play, you get 2 over 9. If you're curious about the proof, here it is. I use chain rule within this proof. I'm sure there's a non-chain rule approach. So I don't know. We'll have to cover that, which is coming. It's coming soon. I don't know when. A few lectures from now. That's it for now. I'm gonna ask you to math on. I'm gonna do the same. See you in the next video.